Let's try to solve right now another example where we want to compute the difference of total head between two tanks linked by a pipe. In this case we have two tanks that are in contact with the atmosphere, tank number 1 and tank number 2. Inside these two tanks there's water and we know its specific weight. These two tanks are linked by a pipe, an inner pipe, where the starting point and the ending one are entering inside your tanks. Okay, so some data. We know in this case that we know exactly the diameter of your pipe, d. The Gauss-Strickler coefficient, Ks. The length of the pipe, L, its dimension. And we know, of course, the kind of fluid inside the tanks, so we know that it's water. We are assuming that the flow is moving inside the pipe following a turbulent regime. Alright, well, in a point inside the pipe it's inserted an instrument called the differential manometer, which contains another kind of fluid with respect to the one that you see inside your system, and playing with difference of pressure, basically, you are able to evaluate the lecture of the instrument, which is the difference between these two interfaces, and this quantity is called delta. So basically we should know the lecture. And this instrument is attached in 2 points of the pipe at a distance equal to little l. Alright, we also know what? We know gamma m. Gamma m is the specific weight exactly of the fluid contained in the differential manometer, and we know L, so the distance between the 2 points where you insert the manometer. Then other data again are Q, because we know in this case the volumetric discharge flowing inside your system. So finally we want to evaluate what? The difference of the two levels. So we want to evaluate epsilon. This is of course epsilon. So our aim is to compute epsilon, and then we would also evaluate delta. Who is delta? Delta is, be careful, because delta is related to the lecture of your manometer, and basically it's the difference between the two piezometric head in the 2 points where you insert your manometer. So in this point you will have a value of piezometric head, and in this other point you will have another value of piezometric head, which means that the difference between these two values gives you delta. Finally, we will also draw the total head line and the piezometric line. So let's start first with the computation of the difference between the two levels. To do this, one can just relate to Bernoulli's theorem again, or rather the extension of Bernoulli's theorem. So let's start considering the first tank number 1, and we want to write Bernoulli's from tank number 1 to tank number 2. So we'll have total head related to tank number 1, which again, remember that is every time is respect a reference system, so you will have that it's this quantity and it's this quantity right here. H1 minus, the flow is entering inside your pipe, so right here you will have a concentrated loss, which is given by the presence of the additional inner tube, and it's equal to 1.16 V to the power of 2 over 2G. So you are entering right here. Then you are moving through your pipe and you will have minus JL. L, remember, is the entire length of the pipe. Again, minus inner tube, so it's again 1.16 V to the power of 2 over 2G. Everything equal to H2. So exactly our Y would be H1 minus H2, which is equal to 2.32 V to the power of 2 over 2G plus JL. Remember again that if you are in the case of turbulent flow, you can write J as Chassis' law, so it's J equal to V to the power of 2 over C to the power of 2 times R, which gives you V to the power of 2 over Ks to the power of 2 times R to the power of 4 over 3. Remember the computation. Then again, for example, I could be interested in this case to write V in terms of Q, since in my data I have directly Q, so I could express this stuff in turbulent condition in terms of Q, and this gives you Q to the power of 2 over Ks to the power of 2 times R to the power of 4 over 3, and then there's the cross section, which is pi g to the power of 2 over 4, everything to the power of 2. Hence, it gives you again Q to the power of 2 over Ks to the power of 2 times R to the power of 4 over 3 times pi to the power of 2 times g to the power of 4 over 4 to the power of 2, which is 16. So, again, it's q to the power of 2 over ks to the power of 2. R is g, because we are talking about a circular pipe, so it's g over 4, so we will get d to the power of 4 over 3 pi to the power of 2, g to the power of 4, and then we have right here 16, and it was 4 to the power of 4 over 3. Hence, if I want to compute this stuff, which is basically a constant because I have pi over 2, pi to the power of 2 over 4 to the power of 4 over 3 times 16 again. This gives you, if you try to compute this stuff, 10.29, just checking the manual, times q to the power of 2 over, then we have right here ks to the power of 2 times g. It's 4 over 3, so it's 4 plus 4 over 3, which gives you again and finally 10.29 q to the power of 2 over ks to the power of 2 times g to the power of 16 over 3, which is 5.33. Hence, we can also rewrite this stuff in this way. It's just another way, but if you feel comfortable to write it like that, it's the same. Usually my suggestion is to compute everything separately, because sometimes when you do many computation, also because maybe you have a simple calculator and not a big computer when you do this thing, it's better to compute everything separately and then aggregate your result to get the only one. Alright. Okay, so let's go on, because basically we have just 1 second. We have just solved our example, so let's try to move this one right here, and let's see what happened. So we are going on with our example. Okay. Okay, so basically we get the point that is h1 minus h2 equal to 2.32 put to the power of 2 over 2g plus up to you if you prefer to write it in a way or another way, but it's, for example, j, which is v to the power of 2 over ks 2 to the power of 2 times r to the power of 4 over 3 times L. Then I can, for example, since this stuff right here, remember that is the difference between the total energy of your tanks. So it's exactly that 1 plus p1 over gamma plus v1 to the power of 2 over 2g minus z2 plus, minus p2 over gamma minus v2 to the power v2 to the power of 2 over 2g. But since in the tank the velocity is equal to 0 because your fluid is in quiet, this stuff and this one goes away, then you obtain exactly z1 plus p1 over gamma minus z2 minus p2 over gamma, which is exactly the difference of your piezometric head between the two tanks. So it's exactly y in this situation. Alright, because p1 over gamma, if you consider, for example, z1 equal to the distance of the free surface, p1 over gamma and p2 over gamma is something that can be erased because your fluid is in contact with the atmosphere, so the relative pressure is equal to 0. Alright, so the first point is resolved because we wanted to compute we wanted to compute exactly y between the two levels. The two levels. Then we want to compute delta. And let's observe that delta. Delta is exactly the difference, and I try to zoom it in this paper because otherwise we won't see anything. So basically delta, if I take the part of the pipe, and it is something like this. So here is my pipe, and inside this pipe there's a manometer, a differential manometer. So you have 1 and 2. Right here. You have the capital delta, which is the lecture of your manometer. Then you have then you have Alright, so sorry for the delay. Then you have basically the difference between the piezometric head in this point and in this point when where you have inserted the differential manometer. So from the lecture you can relate this difference. So there's a formula, and it's possible to compute it, but we won't see how, which gives you delta, which is this difference. So basically it's, if I call this point A and I call this point B, is the piezometric head in A minus the piezometric head in point B. So it's total head in point A minus the velocity evaluated in point A to the power of 2 over 2g minus total head in B minus b to the power of 2 over 2g. But in this point, the velocity is the same, which means that VA is equal to VB, which means again that delta, little delta, is equal to the difference of the total and between point A and point B. But this difference is related to the distributed losses inside the pipe from A to B. And if you remember, we have that the total head from this point to this one. So if I want to draw for a while my total head, respect the horizontal line, it's decrease of j times L, where L is the distance between point A and point B. So basically, little delta is given by j times L. How much is j? I can compute it because I have q. So remember that, for example, also right here, if I have q, q is v times a. So if I want to compute v, I will have that v is q over a, which is pi g to the power of 2 over 4. Once again, I can write this stuff right here, so I will get v to the power of 2 over ks to the power of 2 times r to the power of 4 over 3 times little l. Alright, so this little delta is given because I have v, I have ks, I have r, I have l. Hence, if I want to compute the lecture is related to delta in gamma m minus gamma over gamma times delta, which inverse law. So it becomes that capital delta is equal to gamma over gamma m minus gamma times little delta. And we have finished our example.